Hi everyone, and welcome to Lecture 7 of the Reliable and Interpretable Artificial Intelligence course taught at ETH Zurich. My name is Martin Vechev and I'm a professor at ETH. And in this Lecture 7, we're going to be focusing on another automated certification methods for neural networks, another convex relaxation called DeepPoly. And one other topic that we're going to explore very briefly will be this idea of abstract interpretation, which unifies many of the automated reasoning concepts that we've looked at so far. So just to give you a little bit of an idea of the general theory, where we are coming from. Okay, so let's start. So far in certification, what have we done in the topic of certification of neural networks, right? So we looked at initially we looked at the simple box incomplete certification, which is an incomplete certification method, right? We also looked at complete certification methods via MILP solvers, right? And we showed how to combine the box constraints that are obtained automatically in order to speed up the complete certification, right? Now, because the box relaxation is quite imprecise, although it scales to large networks, we started looking at more involved and more precise relaxation. So in last lectures, we looked at the zonotop convex relaxation, which is actually exact for affine transformations, right? So it can capture the effect of affine transformations exactly, but approximates the Relu activation, right? And zonotops are also an incomplete method, just like box, but in practice they are a lot more precise for certifying and analyzing neural networks. Now, one of the issues with the zonotop was, if you remember, even though it's exact for affine transforms, it was still approximating the Relu. And one motivation for today's lecture will be to look at the convex relaxation method, which has a better approximation, if you want, of the Relu. And in particular, it's going to be strictly better in its approximation. So it's going to introduce a smaller area that approximates the real Relu value than the zonotop convex relaxation. So that's the motivation for today's convex relaxation that we're going to be introducing and discussing, right? So the idea is that you come up with a certification method, automated reasoning method, which is actually more precise than the zonotop relaxation when you are approximating the Relu. And so overall, you should get more precise results. Now, before we go into the DeepPoly, the convex relaxation we're going to look at, I should mention that a lot of these relaxations are instances of these numerical abstractions, right, that people have developed over many years. But there's different ones that people have developed in different, researchers have developed in different application areas, right? This variant of zonotop that we looked at last time, we've developed it in the context of neural network certification. So here on your left, we have the box relaxation. Right? If you want to visualize it, is the most coarse-grained relaxation. Then on the right, here on the top right, we have this relaxation, which we're not going to be looking at in the course. That's actually often used for analyzing programs, general purpose programs, called the octagon relaxation. And it's also a kind of a sub-polyhedra, a more restricted polyhedra, right, with certain constraints that you see over here, right? And then over here on the bottom left, we looked at the zonotop relaxation, right? And the neurons had the following shape that we described here. This we already studied, where we have these parallel lines that are, which are also determined by the number of error terms, epsilons that we have, right? And on the very right bottom, what we have is the general polyhedra, right? So this is the most expressive linear relaxation, right? But it's, in many of these other ones, in fact, all of them, octagons, boxes, zonotop, and in fact, the one we're going to be looking at today, DeepPoly, are restrictions of this polyhedra relaxation. And the reason why people explore these relaxations, right, these more restricted versions of the polyhedra, where we limit the kind of constraints that we can use to shape these limits, right, for what we can describe, is because the polyhedra is actually quite expensive in practice. It's exponential in the number of variables or neurons in our case. So it doesn't really scale to large programs or large networks, but it is still a general, but it doesn't scale, and so this motivates us to look at a lot of these relaxations that may be more approximate, but they're actually much more scalable and can handle bigger networks. And this is quite challenging because we not only have to define the shape of the relaxation, the subpolyhedral relaxation, but we also need to define the transformers, and the transformers have to be, these abstract transformers have to be correct and efficient, right, and scale. So this is just a general note, right? So let's look at the DeepPoly convex relaxation. And just like last time, we're going to have two parts to the relaxation. One is going to be the shape of constraints that this relaxation captures. And the second part is going to be the abstract transformers, which are actually transforming this relaxation, these shapes, okay? So first, let's look at the shape. DeepPoly is a relaxation that we introduced in last year. And since then, it has become quite popular in certifying and proving properties automatically about neural networks. And so deep in front of the poly just tells the fact that it's a restricted polyhedra abstraction to do the setting of deep learning, right? So let's first look at the shape and see what we have here. So let me use our standard annotation here. Okay. So what we have with the DeepPoly convex relaxation is that for each neuron xi, right, what we keep are two constraints. So the first constraint, okay, is like the box constraint, the interval constraint, just that would keep also if we just analyze with boxes, okay? And so we just have a lower bound for the given neuron, Li, and then we have an upper bound, Ui, for the given neuron xi. So that's two constraints that we keep, or one interval associated with each neuron xi. But the more interesting part that we keep are these two relational constraints, okay? And we'll see why we say relational. And so the first one is, again, a lower bound. So we have some lower bounds. So xi, the neuron, is greater than some expression ai, and it's denoted that it's a lower bound here by this sign. So x is greater than or equal to this ai. And we have an upper bound also, some other constraint here, which xi is upper bounded by, okay? So this sign here, then also upper bound, okay? And so what we have here is that, okay, these expressions, AIs, right, are just, forms affine expressions, okay, over here, these linear expressions, okay, just some product of these terms over here, and this is some coefficient over here, and this is some other neuron over here. You can think of it as we'll see later. These xj's here are just going to be, for all practical purposes, the neurons in the prior layer, but it could be in some layers even before xi. So anyway, what we have is for each xi, we have these relational constraints, and one relational constraint is going to be, it's called relational because, we have these xj's here, okay, and the different xi's are going to be potentially sharing this xj, so we're relating them essentially, as you see. So we have these two constraints that we are lower bounding and upper bounding our neuron, okay, in addition to the interval constraints. And we'll see an example to make this more clear. So let's clear this and look at some points. So this is the shape. So we just have 4 constraints per neuron, 2 interval constraints and 2 relational constraints. Okay. And so a couple of points here that are important. So this DeepPoly relaxation is a subpolyhedra relaxation, meaning it restricts the general polyhedra, so it is less precise, right? It may introduce more points that don't exist, but this restriction that we've outlined here is actually good for obtaining more scalable analysis, more scalable certification, okay? In addition, as I mentioned already, this relaxation captures affine transformations exactly, just like the Zonotop. And also, we introduced abstract transformers for the Relu, sigmoid, tanh, maxpo, and so on activations But what's important for us in the lecture especially is looking at the Relu activation and relating that Relu activation to the zonotop activation, so we can kind of compare the two. And so nothing surprising, one part is the shape, another part is the abstract transformers that transform this shape, right? Okay, so when I say that it is DeepPoly and generally this polyhedral relaxations, the reason why we introduce them is because they lose a little bit of precision, but they turn out to be a lot more scalable. And what by scalable it means, they have better asymptotic complexity algorithms. So if you look at here in this little table that I put, is we have the transformer, the abstract transformer for affine or for Relu, right? And n is the number of neurons that we have, m is the number of constraints of the the transformer for the particular neuron xi that has to produce the shape for xi, okay? And W max is the max number of neurons in a layer, and L is the number of layers in the network. And so one single neuron transformer, the complexity of a single neuron transformer just to produce the shapes that we outline above for xi, for polyhedra, this would be for affine would be O nm squared, okay? We're not going to get into the details of the polyhedra because we're not studying the polyhedral relaxation, but it's good to kind of compare the two. And if you look at the, more interestingly, at the Relu relaxation, what we see is that it's exponential, essentially, in the number of variables and the number of constraints that we have. So the polyhedra is actually very expensive, the general polyhedra. So it will not really scale to big networks, maybe 3 by 50, 3 layers by 50 neurons. It's really small networks. If we look at DeepPoly, however, its complexity is quadratic times L, the number of layers of the maximum number of neurons in a layer, okay? And Relu is actually constant. So the overall complexity here is actually much better for the DeepPoly relaxation. And this is its main advantage over the polyhedra, while hopefully not losing too much precision in practice. Okay, and so this direction of coming up with clever convex relaxations of the general polyhedral domain so that they scale to large networks without losing too much precision is a very active area of research, right? So there may as well be other relaxation beyond the zonotop one we showed and the DeepPoly that also can give you good results while scaling to realistic networks. Okay, so just a reminder, now that we've looked at the shape of DeepPoly, right? So just a reminder for the box, we are going to be using this network here, this our toy little network, where we have two inputs, x1, x2, maybe these are pixels, and then we transform them with an affine transform, then followed by a Relu, followed by an affine transform, followed by a Relu, followed by an affine transform, right, to produce the output neurons x1 and x11 and x12. Okay, and if we use the box, we're going to end up with the following constraints, just a reminder. And the property that we want to prove here is that x11 is greater than x12 for all inputs that x1 and x2 can range over, and these are the -1 and 1, as we see here on the left, right? And if we can prove this, then we'll probably know that for any input in x1 and x2, the network is going to classify it to the label of x11, right? Whatever that label would mean if you have binary classification to the first label, okay? And so, as we already showed before, and if you look at the results here, you can see that -0.5 and 5 in x11 and or 0.02, interval 0.2 for x12 that is obtained with box for x11 and x12 respectively, actually is not precise enough to prove the property that we want, okay? And so this motivated us to look at better convex relaxations, and now we're going to see how the DeepPoly convex relaxation helps us prove the property that we want by computing more precise results. But this is the network we're going to be using for illustrative purposes. Okay, so let's begin describing the DeepPoly convex relaxation. So what we have here is, again, we have x1 and x2 ranging in this range -1 and 1. And so remember, with every neuron in the network, including the input, we are associating these constraints, these 4 constraints, the concrete lower bound, the concrete upper bound, and then the the symbolic lower bound and the symbolic upper bound for the particular neuron. So if we start with x1 over here, we see that because x1 is in the range -1 and 1, these are obtained directly. So x1 would be greater than or equal to -1, x1 would be less than or equal to 1. This is what the interval says. So the lower bound for x1 is -1 and the upper bound for x1 is 1. And similarly for x2. Okay, so we obtain our first results over here. Now for the next, and let's use our little notation here. For the next step, over here we have an affine layer, okay, and also like in the zonotop, this is captured exactly here with the DeepPoly. And so what we have here, let's see what we're going to have here. Well, what we know is that x3, let's look at x3 now. We know that x3, the constraints, the symbolic constraints associated with x3, the exact transformation would be x3 is equal to x1 plus x2, because the bias is 0 over there, so nothing happens. So it's going to be x3 equal to x1 plus x2. But we cannot represent x3 equal to x1 plus x2 directly as equality in the DeepPoly relaxation. We have these inequalities. And so we can just write this information down as follows, which is what we do. We say that x3 is greater than or equal to x1 plus x2, and x3 is less than or equal to x1 plus x2, which together imply this equality. So we can express the same information in this way, that x3 is equal to x1 plus x2 with the following symbolic constraint. The lower bound L over here and the upper bound symbolic constraint. Okay. Now, one question is, and we're going to be studying that, is how do we obtain these bounds over here? Okay, so we were good with the affine transform. We captured it exactly using our, we captured it exactly in the DeepPoly. But how do we obtain this L3 and U3 here, right? And so if you look at, let's look at the lower bound. And so L3, okay, over here, L3 is equal to -2. How do we get -2? So let's look at x3, the symbolic expression x3. Well, x3 is greater than or equal to x1 plus x2. It's lower bound by x1 plus x2. And if we see what the lower bound for x1 is, the lower bound for x1 is -1. And the lower bound for x2 is -1 over here as well. So we have -1, -1, we get -2. Okay. And similarly, we can do the same thing for U3. If you look at how do we obtain U3, well, we can just look at the x1 plus x2 and look at the upper bound. So the upper bound for x1 is 1, the upper bound for x2 for x1 is 1, for the upper bound for x2 is 1 as well, so 1 plus 1, 2, and we get that upper bound here. We're going to be discussing a little more how we obtain these bounds here. For now, keep in mind that how we obtain these L3 and U3, how we obtain the concrete lower and upper bounds, is going to be one of the more important features of this relaxation. Okay. So the key point here is that we managed to capture the affine transformation exactly in the DeepPoly relaxation. And similarly, we're not going to go over this, but similarly, you can capture x4. Same thing with the inequalities here, that you can capture the equality that x4 is equal to x1 minus x2. Okay, and the same way we obtain the L4 and U4. So the affine convex relaxation is just like in the zonotop, is actually quite easy to capture exactly. And this brings us to the next layer. And as we know from the zonotop discussions before, this is usually which is a little bit more challenging. We need to capture the max, the Relu convex relaxation, the Relu activation with our particular convex relaxation. So let's see how we do this, okay? And then once we know how to do that, we'll be able to analyze the entire network. So let's see how we capture the Relu convex Relu activation. So what we have here, remember we're in the single neuron transformer case where xj, we know the output y equal to max 0 xi or xj here, has to be obtained by whatever constraints we have associated with xi. And what we're going to do, just like in the zonotop case, we're going to be defining the transformer for this Relu activation, but just using the AY and UI, the concrete lower and upper bounds which are associated with this neuron xi. Okay, so let's look at the three cases, and these are the same cases as we had with the zonotop. So what we have is the strictly negative case, where the upper bound of this input neuron xi, okay, the upper bound is less than or equal to 0. If it is less than or equal to 0, then everything is going to be 0. So that's not surprising. Okay, so xj is just going to be 0 in the concrete, so all the bounds become 0. Okay, if the lower bound of xi is greater than or equal to 0, which means, of course, the ui is also going to be greater than or equal to 0 because it's greater than or equal to li, then everything is strictly positive, right? So we're in the positive case. And what we have here, we know in that case that xj is going to be xi, okay? And so we just take the constraints from xj. It's going to share the same constraints. So whatever constraints ay and ui were for xi, the same values are going to be true for xj. And it is because xj is going to be xi, right? Then we can have the upper bound, xj is going to be less than or equal to xi, and xj is going to be greater or equal to xi, thereby capturing equality. And this is what this thing says here. Okay, right? So both of these are going to be xi, and together it captures the xj is equal to xi. All right. So this is in the negative case, and this is in the positive case. Okay. And now we come to our most interesting case, the crossing Relu case, meaning that the lower bound is less than 0 and the upper bound is greater than 0. So now we are in this crossing business and we need to see what to do. Okay. So let's remind ourselves what is going on here. So what happened here, remember that you have the exact Relu, which is over here. Just use our colors here. Maybe use another color. We're right here. So this is the exact Relu, and some works can capture the exact Relu, like this one over here, Reluplex, but it of course doesn't scale. It works for very, very small networks. Okay? So this motivates this looking at more coarse-grained approximations of the Relu, like the box. This we already looked at before. We discussed the optimal single neuron convex approximation of the Relu, the triangle approximation, right over here. But this also doesn't really scale to realistic networks, and this motivated us to look at greater relaxations, bigger area. And this is the relaxation that we actually looked at last time. This is the deep Z relaxation, and the same shape and the same transformers are described in a different way in other works, right over here by Eric Wong. And so ultimately the deep Z or the zonotop convex relaxation, we call it deep Z here, like DeepPoly, because it is a zonotop but has specific transformers in the deep learning setting. And this was the Relu approximation that we studied in the last lecture. Okay. Now, basically, what we have now is let's use this here. Okay. So what we have now is we're going to introduce this DeepPoly relaxation for the Relu, and it's going to look like this. So this is what we looked at last time. This shape approximates it, right? And we discovered the constraints. We discussed how to compute the lines, how to define the transformer. But now let's look at the DeepPoly. And so what happens in the DeepPoly is the following situation. Now DeepPoly, because of its constraints, can actually represent shapes that are not zonotops. So you can see this shape over here that we're looking at, right? Like this one over here, this thing over here. This is not a zonotop. This blue triangle over here is not a zonotop, okay? And so because the shape allows more rich, the constraints allow more rich shapes. Okay, so we're going to look at this relaxation here now in the next slides. okay, with the DeepPoly that approximates the Relu. The paper also explores this relaxation here. The two relaxations are non-comparable. One includes points that the other doesn't, and the other way around. Okay, but both of these relaxations here, this relaxation and the one here on the right, actually have smaller area in the shape than that's the zonotop approximation, the deep Z approximation that we looked at last time. Now, the fact that it has smaller area, they're still non-comparable. If you look at this one and this one, right, there are points here somewhere which don't exist in the zonotop, and there are points here in the zonotop that don't exist in the DeepPoly. Okay, but it turns out when the area is a fairly good heuristic, when the area is smaller, that it turns out that in practice it tends to produce more precise results. DeepPoly in practice is almost always more precise than deep zonotop, deep Z, even though they're technically non-comparable, but somehow the smaller area helps it to be more precise, includes fewer spurious points, let's say. Okay, so we're going to look at how to derive what the Relu transformer here are, and they're actually pretty straightforward. You can actually from that pretty much derive the transformer by yourself for this shape over here. Okay, and which shape do you actually pick when you're analyzing a neural network is a heuristic. You can look at the areas, this area over here, and this area over here, and then pick the smaller area, and then decide dynamically during the verification which approximation you'd like to choose. Okay, and as I mentioned already, both of these shapes, no matter which one you choose, are actually smaller area-wise than the zonotop Relu approximation. Okay, so let's look at this one here and look at these transformers. And remember, we actually already defined the line, this line over here that I'm highlighting now. We actually derived this line already when we were looking at the zonotop approximation. It's the same line over here, okay? But let's look at it anyway, how we derive this DeepPoly Relu relaxation. Okay, good. So let's look at it here. So what we have is, again, we have this thing, just to remind you, on the left. And with our neural network, what we have are the following expressions on our over here. So now let's look at how would we derive the shapes for X5 over here. Okay, so what would the shape for X5 be? And so clearly what we see is that the resulting X5 has to be under this line. So it has to be under this line, but it also has to be greater than 0. Okay, so we already know how to compute this line. We already discussed it last time, right? We have the slope, this divided by ux minus, so ux divided by ux minus lx, right? Plus shifting the line by a value in order to go from, say, this line over here that we looked in the case of zonotop to this line over here, because we already computed this line. We know how to do it. Okay, so let's look at it here. So what would we get? Right, so what we get here is what you would expect to get. You have that over here, right? X5 has to be greater than 0. So let me just use another. So you know that X5 has to be greater than 0. Okay, so it has to go up. Okay, so this is this one that I just highlighted there. And then we know that X5 has to be less than whatever that line is. So what is this line over there that we already discussed? Well, this is going to be the slope, which in our case is, so let's highlight. So we have that L3 is minus 2 and U3 is 2. And so we know that we know the length of this line over here, okay, and we know that this value here, know that this value here is going to be 2, okay, and so what we have here is this line over here, okay, which is 2, okay, divided by this line over here, which is, so this is 2 and this is 4. This is the length of this line over here. So we have 2 divided by 4, and so this is 1/2, and so that is how we get our 1/2. Okay, over here. But because we know we need to shift this line, up by 1 here. Okay, we need to shift this line up. Okay, so we have this line over here. Okay, they have the same slope. This line that I drew and this one have the same slope, but we know that we need to shift this line by this value over here, which in our case is 1, in order to get our line that we need. This is 1 over here. And so that's how we obtain this line that we want. This is exactly the same line that we obtained when we were discussing the zonotop approximation. There is no difference. Okay, so this line is the same as the zonotop, so same as zonotop. And the other line, which is this bottom line over here, okay, this one over here, right? So let me just highlight it maybe in another color. Okay, let's pick this color over here. So this line, this one that I'm highlighting, the green one over here, this is the 0. And so that's how we end up with the x5 is greater than 0. And this is going to capture our shape, combined with the fact that, of course, xi is between lx and ux. Okay, so that's how we obtain this shape over here via these constraints. Okay, okay, so that's how we obtain this. The next question, could be, how do we obtain this, values over here for L5 and U5? Okay, so again, you can do the calculations. So L5 is the lower bound, okay, and we know that the lower bound is greater than or equal to 0, so we can just take it from here. The upper bound is some expression over here, right? So you 0.5 times x3 plus 1, and so you have 0.5 times the upper bound over here 2. So you're going to end up with 0.5 times 2 is going to be 1, plus 1 is going to be 2. Okay, so that's how we end up with this lower bound L5 0 and U5 being 2. Okay, so very similar to the zonotop, except that we have this line over here, okay, horizontal line to capture the 0 being greater than or equal to 0, and the upper line we capture it directly with the constraint 0.5 times x3 plus 1. Okay, so we then don't have to deal here with these error terms or introducing error terms or anything like this. All right, so really it's constant amount of work because we just compute the slope and then we get our expressions directly. Okay, so let's similarly, let me just clear this so that we don't. Similarly, we can obtain the values, the expressions for x6 using the shape that we want. So that's how we obtain our two shapes over here. So these two shapes, we obtain them by just talking about these lines over here and about this line over here. Okay, all right, for x5 and x6. Okay, great. So this is great. This is how we compute our Relu transformer, Relu abstraction, Relu relaxation for the DeepPoly relaxation. Okay, so this looks fairly simple. For the Relu, we just care about, about really what we care about is by looking at the L3 and U3, this concrete lower bounds for the previous neuron over here. We use them, to obtain our, this L3, U3, LX, UX, and we directly use them in our calculation. Before with the zonotop, we had to take the zonotop and we had to, make a linear pass over the error terms in order to compute the interval concretization of the zonotop. Now we don't have to do this here. Our life is much easier because this L3, U3 are actually kept as part of the lower and upper bound values that the previous neuron can take. So we don't have to worry about this. We just take our whatever values are there. Now, of course, you see something important here is that, as we know, this range over here, this L3, U3, is going to be important for getting more precise results. So if we have more precise L3, U3 that we have obtained, then we're going to get a tighter approximation of the Relu as well, because we're just going to have a tighter shape over here. So maybe they will not be here, but they will be here. So we have a tighter values. So one challenge here in the DeepPoly, so for as far as the Relu goes, the Relu transformer just consumes these values. But the challenge here is how do we get, as tight values as possible over here, okay? Because these values themselves may not be so tight. They will be sound, they will be correct, but they may not be, the real interval may be -1 to 1, but we just put -2 of 2 because of computational challenges. So what we need to discuss next is how do we obtain this tighter LUU3, because they can affect our approximation of the Relu transformer with DeepPoly, right? We said that the affine is exact over here, but this computation of the L3U3 are actually central to the precision of the Relu, and of course the particular approximation that we're choosing here, this one or the other one on the previous slides. So let's discuss this a little bit. How do we get a more precise LU bounds that we can then use to compute a more precise Relu approximation? And so this brings us to the affine transformation again. All right, so the affine transformation is, as we said before, so let me just take this, the affine transformation is as we said before, right? So if we look at our example here, we have these neurons x5, x6, and we're going to be computing the constraints for x7, so we have an affine transformation over here. And so we know that, this is going to be x7 is equal to x5 plus x6 minus 0.5, because the bias is minus 0.5. And so, this is the exact computation of exact representation of this expression x7 equal to x5 plus x6 minus 0.5, except that it uses these constraints over here too, because we cannot have the quality in the Convex relaxation. So we capture it exactly, but the question is, what are these bounds over here? Okay, how do we obtain these bounds? And when we showed it last time, like a few slides ago, we just said that we, let's just look at x5, look at its bounds here, take L6, look at the bounds here, and just compute it, right? So that's one way you can do it. And this way is going to be correct. It is going to be sound. There is nothing wrong with it, okay? Everything is going to be sound and certified and so on, but it may not be as precise as you want, okay? And so let's see a little bit here what is happening. Okay. So let's see over here. And this is what I said, right? You can take, let's say that you can compute the upper bound for x7. One way to just plug in the upper bounds for x5 and x6. So I can just look at x5, its upper bound is 2. The upper bound for x6 is 2 as well. U6 is 2. So I'll just have 2 plus 2, which is 4, minus 0.5 is 3.5. And I can just say, hey, well, the UZ upper bound for XZ is 3.5. And that would be completely sound and correct. But it might not be as precise as you want. So this is what we would obtain by just substituting the U5 and L5, in this case, U5 and U6 into this expression for x7 less than or equal to x5 plus x6 minus 0.5, and would end up with this value of 3.5. But unfortunately, while sound, this value is actually not, this value is for L7 and U7 obtained in this direct substitution way are not as precise as you want them, as they could be, right? Okay, so let's see now a little bit what else we will do and why. And so the idea here, and let me highlight this because that's important, is one of this over here. This is the idea of back substitution. Okay, so we have this idea of back substitution. So rather, we want to compute this L7, U7, but rather than just plugging in, using the previous constraints over here, okay, these concrete values, what we do is we actually substitute back the constraints. Okay, so we have this constraint, we have x5 plus x6, and x5 has some bounds, okay, over here, and x6 has some bounds over here, okay, and similarly for the upper bound. So rather than going with the L5, U5, L6, U6, let's just instead substitute back the expressions, the lower bound or the upper bound, depending what we want to compute, for this x5, x6, okay? So let's do that and see what happens. So if I substitute this expression, what I had for x7, which was a function of x5 plus x6, right, with whatever is, let me just highlight this here. Okay, so what we had is we had the expression x7 is less than or equal to x5 plus x6 minus 0.5. And so what I did is I substituted x5, we are trying to compute the upper bound here. So I substituted the x5, we had an x5 here before, I substituted it with this expression, which is the upper bound for x5, right? Because I'm trying to compute here the upper bound, the u7, right? So let me do that. Let me compute a symbolic expression here. So I just took this one over here, right? And so I had u5 0.5 times x3 plus 1, okay? And I similarly substituted the for x6, which I had before, I substituted the 0.5 times x4 plus 1, okay? So this is going to give me 0.5 times x3 plus 0.5 times x4 plus 2. But because I had minus 0.5 here, it becomes 2 minus 0.5. So just plugging back the symbolic upper bound expressions for this x5, x6 in order to arrive with this equation over here. Well, now I have something which is a function of x3, x4. So if I have something which is a function of x3, x4, I could, take the upper bounds that I have, the u3 and u4 for x3 and x4. I could do this, and I'll obtain still some sound results. But if I want to be even more precise, I would substitute back the values for x3 and x4 all the way to the first layer. So let's see a little bit what happens over here. Okay. So if I replace these bounds, okay, what I'm going to end up with is with this expression over here. Okay, I'm ending up with this expression over here, and my goal is still to compute this u7, because I want to compute the upper bound here, the concrete interval, because I know that these intervals L7, U7 are going to be very important for me for the Relu relaxation later to get a smaller area after all. So well, we have the following situation. Let's look at our network. Now it's a function of x3, x4. Okay, so well, let's continue this substitution back to the first layer. Or in the first layer we have the input layer, right? And so what we can do now is do the same thing. So we have the x3. Let's substitute back x3. For x3, we place x1 plus x2, because x3, where is x3? x3 is upper bounded by x1 plus x2. So we just keep back substituting the symbolic upper bounds. And similarly for x4, I'm substituting x1 minus x2, because I know that x4 is less than or equal to x1 minus x2. Is over here. Okay, and if I do this back substitution, I'm going to end up with the following expression, x1 plus 1.5, okay? And I know that, x7 is less than or equal to x1 plus 1.5. And then finally, I know that x1, I'm all the way to the beginning. I know that x1, now I can use this bound over here. Of course, I can use this one over here, x1, but they're the same. So I can just plug in the U1 here. There's no problem. It's the same. And I'm going to end up with this x1 is 1. That's the upper bound. x1 is less than or equal to 1. This I know, plus 1.5. And so I end up with x7. Okay, the upper bound for x7 is 2.5, right? And this is it. So we're going to end up with 2.5 over here, right? And this is a tighter result than simply plugging in the L5 and U5 or L3 or U3 from before, right? And the reason why this happens is because this back substitution is exact, essentially doesn't lose information, but the intermediate upper bounds, because we represent them as intervals like this, right? These guys, they lose a little bit of information, right? They lose they're a little bit imprecise, And so by using this symbolic information as much as possible, back propagating to so this is not to be confused with back propagation in the typical machine learning training jargon. That's why I like to call it back substitution and not back propagation. Some people call it back propagation, but we shouldn't confuse it with that. This is just substitution back, just simple algebraic substitution all the way to the first layer. And this is how we obtain our concrete L7 and U7 bounds. And this is it. This is why the affine transformation had the complexity that it did, that we showed in some of the earlier slides, right? The main complexity in the DeepPoly is in this back substitution business all the way to the beginning. Now, in practice, of course, if you have a very deep network and you have many of these substitutions, you may not go all the way to the beginning, but maybe you stop. Maybe you could have stopped, even over here, and just use these values here because you don't want to back substitute all the way down. The deeper you back substitute, ideally to the beginning, the more precise results you're going to obtain. But if you back substitute only one layer, you're still going to be sound but lose some precision. If you back substitute two, you're going to be a little bit more precise, and so on and so forth. Okay, so this gives you the idea, or gives you the definition essentially of how the affine transformation works. So you capture the affine effect, right? Exactly, and then you just back substitute all the way to whatever layer you believe you get precise results, ideally to the beginning, to the first layer. If it's too expensive or your network is too deep, you can back substitute maybe to some of the, maybe a couple of layers or 2-3 layers back and get some, or you can back substitute differently depending on the particular neuron that are in, if you have some heuristics like this. But the important bit is this back substitution in order to obtain more tight bounds for L7 and U7. Okay. All right, so I hope this gives you a clear idea how the affine transformation works, right? And the affine is exact, but it uses back substitution to compute these concrete bounds in order to use these bounds later in the Relu approximation, okay? All right, good. So that's the results that we get by using back substitution, tighter U7, and similarly we can obtain the L7, this L7 bound. You can do the back substitution yourself. Well, in this case, the L7 is actually trivial because the X7 is already bounded by concrete value. But you can have other examples where you also have to do the back substitution for X7 as well. And in your project, when you do the project, you have this kind of networks where you have to back substitute both the lower and the upper symbolic upper bounds. Right. So the complexity of the back substitution, the asymptotic complexity is what I mentioned. This is the W square max. W square is the maximum number of neurons in the network, number of layers. So that is the, so when we say the back substitution is pointwise, it means that if I have multiple neurons for which I have to compute this constraint, right? For instance, if I have another neuron over here in the same layer, which I do in our network, okay, I had X8 here, then I can do this back substitution in parallel. I can compute, X7 constraints and X8 constraints in parallel, so it's pointwise, okay? All right, now one additional point here is that whether, because of something a little bit more technical, because of this relationality of constraints and whatnot, when we do the back substitution all the way to the first layer, we plug in the, we obtain these bounds over here for U7 and L7, this may still, this may still not be the tightest bounds that you would have obtained if you had actually used the linear solver and you had given it all the constraints that you have in the network so far, all of these constraints, if you had given it all of these constraints that you have here, and you had asked it to compute the tightest L7 and U7 possible, right? So there is also that, because we can discuss this more, but this is also because of the approximation of the Relu, right? This is not such an important point, and in practice, doing more on top of the back substitution actually doesn't bring any precision gains, even though in theory it may, but in practice it doesn't seem to be the case. In practice, back substitution seems to be a very good and efficient way of obtaining tighter L7 U7 bounds, and it's also easy to implement. Okay, so just a couple of points here. Okay, so if we do what we showed, all right, so we keep this convex approximation for the Relu that we discussed, like with this triangle there, right? This right triangle, we're going to end up, the following expression. And if we do back substitution, then we would end up with all of these expressions over here for our network, right? In DeepPoly shapes, if you like. Now, of course, the fact that we ended up with these shapes, that's fine, but what we're interested in was proving that X11 is greater than X12, meaning that the network for any value in the range X1 between -1 and 1 and X2 in -1 and 1, the network will always, for any of these points, it will always classify, it will always select the label associated with X11, right? So X11 has always greater value than X12. And we couldn't do this with the interval or with the box relaxation because it was too imprecise. So we want to prove this robustness property, this safety property. So what we have here is, again, we're given our constraints here, right, at the last layer for X11 and X12, right, and then we want to prove that X11 is greater than X12. So essentially, the the subtraction of X11 minus X12 should be provably greater than 0. Well, that means that this value has to be greater than 0. Okay, so the lower bound of X11 has to be for sure greater than the upper bound of X12. Okay, which is not the case here, if you see. Okay, and so if we just use again these bounds over here for X11 and X12, if I just use these bounds over here, this one over here for X11, and use these bounds for X12, then you're not going to be able to prove our property. Okay, oops, we're not going to be able to prove our property. We're going to end up with the value minus 1.5, which is essentially the lower bound, right, here is 0.5 minus the upper bound for X11, for X12 is going to be 0.5 minus 2, and we're going to end up with minus 0.5, which is clearly not greater than 0. So we are not going to be able to prove our properties. So what should we do? Well, what should we do is what we already know how to do, which is back substitution. So we can just, back substitute again. Of course, if it works, in this plugging in of the concrete bounds, you can use it. But if you fail, then you can back substitute. So again, you can, for X11, you can use, you can take these expressions over here for X11 and X12 and start back substituting the value of X9, X10, the symbolic constraints for X9, X10, X10 over here, and so on and so forth, just like we showed before. And then you'd end up with bounds for L1, L11, U11, L12, and U12 that when you subtract it, L11 minus U12, you're going, the lower bound for X11 and the upper bound for X12, then you're going to end up with 0.5, which is strictly greater than 0. And so you have managed to prove your property. So the only point here is if you fail to prove the property at the end by just using this L11, U11, L12, U12, these concrete values when plugging it in, then that's fine. There is still hope. You can still back substitute. Maybe you back substitute one layer or a couple of layers. Maybe you're able to prove your property. If you can't, you can just keep back substituting back to the beginning. And maybe you'll be able to prove the property. If you can't, then the relaxation was not precise enough to prove the property of interest. It may still hold, but you are not able to prove it, or it may be that it really doesn't hold, right? Okay, so I hope that this gives you a clear idea how the DeepPoly relaxation work. It is conceptually clean when you do the convex approximation for the Relu. you are approximating the triangle, right? And you get this right triangle that we looked at here. And one of the lines was already the line we looked at, the deep zone with the zone on top. The other one is the line greater or equal to 0. The affine, the precision of the Relu relaxation depends on the L and the U concrete bounds that you're using from the previous layer. And so you want to get them as tight as possible. And then the affine transformation, which produces those bounds, can be captured exactly in the DeepPoly relaxation. But to get tighter bounds, these L and U bounds, then you employ back substitution on the symbolic expressions that you have potentially all the way to the beginning in order to obtain good LU bounds that you can give to the Relu activation. And that's how the DeepPoly approximation works. Because the Relu is strictly better area, its approximation is strictly better area-wise than the zonotop approximation, it also tends to produce more precise results in practice, right? While still being much more efficient than general. It strikes a good spot in the trade-off between precision and scalability. Okay. Let's get rid of this annotations, so I'm not bothered by this. All right. Okay, so this discussion here really completes our this whole foray into the automated reasoning for deep neural networks. We looked at the box abstraction. We looked at the zonotop approximation, specifically the deep zono, which is the deep Z, which is a zonotop targeted for deep neural networks. We looked at the DeepPoly. We looked at its abstract transformers. These were all incomplete methods. In other words, if the property holds, they may not be able to prove it. But if the property doesn't hold, they will certainly tell you that it doesn't hold, so that they are definitely sound, but may not always be able to prove the property. And this whole idea of getting better and better, more precise convex relaxation while keeping them scalable is still a very active area of research. And these deep Z and DeepPoly are some of the more used relaxation today for analyzing neural networks, but of course other relaxations are always possible, other sub-polyhedral relaxations, right? So this gives you a pretty good coverage of what is going on in certification. We also introduced a complete method, right, based on mixed integer linear solvers, and we showed how to combine it with the box convex relaxation in order to speed up the certification, okay? And so this gives you a very, very good basis on certification, on deterministic certification of neural networks. It's still a major challenge how to scale these methods, although they are now scaling to quite large networks, especially as we'll see later when the network is actually pre-trained to be more provable with some of the certified defenses, or even with the PGT defense that we looked at already. It is you can prove a lot more about it than if you just take a untrained, if you just take a normal network which is not adversarially trained. Okay, which kind of makes sense if you bias it towards provability, towards some property holding, even experimentally, then you can hope to prove more when you actually employ this mathematical relaxation, this mathematical certification techniques that we look at. Okay? So much more remains to be done in this space. It's a very interesting space, active research. Now, before we actually conclude our discussion of deterministic certification of neural networks, I wanted to mention to you, the general theory that these relaxations really are an instance of and where they're coming from. Okay, so that is not all in vacuum like this. Just so that you have a more broader education idea where things are coming from, what the history is, and how things appeared. And so this theory that we're going to be looking at, a very particular attention is paid to what sound means. Okay, what is correct? We always use this term to be sound, but we need to define really mathematically what sound means, what optimal and exact actually mean. Okay, so let's look a little bit at that theory so that you have a broader understanding of the general subject of automated certification, both for neural networks and in general. okay? And so if you pop up and if you look at the problem that we're trying to solve, we are given a property like robustness, and we're given a program like a neural network. And what we're trying to do is we want to build this certifier or verifier of neural networks, right, or some programs, which can just take the property in the program and just say whether the property holds, or if it doesn't, to give us a counterexample, okay? And so we know, due to Rice's theorem, that actually this is impossible to build such a general verifier which takes any program and any property and always tells you whether property holds or it doesn't. So the general problem is undecidable, okay? And this is why this pushes us to a lot of these approximations that we're looking at in the first place. Now, neural networks are more restricted programs. For instance, they typically don't have loops associated with them, so you don't have to worry about fixed point computations and things like this, widening and this terminology that we're not really going to be looking at here. And so in that case, you can, in this more restricted setting, you have a hope of employing these complete methods like we looked at. But of course, they also may not scale in practice, which motivates us to look at these approximations and these convex relaxations. And so this theory of how to represent an infinite number of behaviors or a very large number of concrete behaviors into a finite mathematical representation and to transform this representation in a sound way, like for instance, a DeepPoly shape or a deep Z shape or a box shape, and how to transform this is dealt with by a theory called abstract interpretation, which is really a theory of approximation of how to approximate computations, okay? And I would say that this is one of the most elegant theories in computer science that I have seen, right? It was introduced in the late 70s by Patrick and Rodier-Cousseau, and it's a very elegant theoretical frameworks for reasoning about computation in general, and representing, as I mentioned, infinite number of behaviors in a finite manner and transforming them. So representing them in the computer and transforming them in an optimal and exact manner, right? Way. So the theory was introduced in the late 70s, right? And their entire course is only on abstract interpretation. That's not really something that we want to look at in the course here. We just showed some instances of it with these relaxations that we looked at. The theory started gaining more popularity in the 90s, where most major static analyzers that are used in practice are some form of abstract interpreter. In fact, all of the convex relaxation we looked at so far are form of abstract interpretation, right? And so the principles of abstract interpretation are very fundamental to reasoning about computation, as I mentioned, with infinite or very large state spaces that you cannot just enumerate, okay? And one way I could have presented you the material is to go over the entire abstract interpretation theory, and we'll spend many lectures and then show you particular instances, but this would be beyond, I think, what would be too much for our course. It's not something that we really need in such detail here. So we chose to go the other way around, but it's just good for you to be aware of this theory, okay? And so abstract interpretation concerns itself with questions such as, what is it that you are approximating? When we talk about approximations of relaxations, like what actually you're approximating, what does it mean for an approximation to be optimal or to approximate something? What does it mean to be sound and correct? And how do you actually build correct and efficient analyzers of verifiers, like in our case for neural networks, right? And interestingly, can the process of building these verifiers be automated? Is it a constructive theory? And in fact, it is, where you can start with the mathematical definition of of your transformers, if you like, or of your, we're not going to have time here, but of your concrete semantics, and to derive the abstract transformer automatically. It's not something that we're going to be looking at here. It's too general for our purposes, but that's something to be aware of, okay? So let's just summarize some of the key concepts of abstract interpretation here in just a one-page cheat sheet. It's really something we can talk about for many, many lectures, but let's just summarize it here so that you can get a little bit of an idea. Okay, so what you really have here is you have in orange over here, this set over here, we have this set in orange. Okay, so this is just some concrete set. So in our case, it could be, for instance, it could be, so this set here in orange is denoted as X. So this could, for instance, be the range that the neurons, the inputs of the network can take, right? So this could be the L infinity bow that you put around the input image, right? So this is all the possible images here in orange that are there, okay, in the concrete. And so what you can do, mathematically speaking, is you can take each of these images, like each of these points here, lots of points, okay, here, and I can run them through my neural network, F, right, just concretely, and I'm just going to end up with lots of points over here. I'm going to end up with lots of outputs, okay, so that's what I can do, and this is this output region here. So that's a good thing, but of course we cannot enumerate like this. We cannot enumerate in this way, and so if we could enumerate, we could just take this f of x here, where x is the the concrete set, and we just enumerate every point. We'll end up with this funny shape here. It's a non-convex here, but you cannot do that. And so what we did instead, we represented the this massive set of concrete points via some approximation, some symbolic shape. Could be like a box constraint or some other shape. Could be the L infinity box around the image called Z, and now that's a symbolic shape. So we never actually enumerated, and we just took the symbolic shape that is in blue here, right? And then what we did, we took the symbolic shape which is in blue, and we symbolically transformed it into another symbolic shape, another blue symbolic shape, and we denote this by the function f sharp. And our concrete transformers, if we would have just run a point here, that would be like applying the whole neural network, and then we're getting the points here for every point. And what this funny thing here says is, well, these are your abstract transformers. This is just your Relu affine transformers that you have for a neural network, where you're just applying it on the symbolic shape. So the f sharp is nothing but the symbolic version of the concrete activations that you have in your network. And what do you get? Well, you get the shapes over here, this funny shape over here, this blue shape, and that shape is not is more approximative than this one over here, okay, the one that you would get in the concrete, because we lose some precision, as we saw already when you do the relaxation, right? And so this picture here captures the essence in a sense. So what it says is, if I have taken if I have taken these concrete points over here, this thing is actually, which is the orange region, this is actually a subset of the results that I would obtain. Of course, it's smaller, so this is soundness, right? Than what I would obtain if I apply the abstract transformers, okay? Because I lose some precision when I apply this F sharp. And the funny thing here is, the important bit here is this gamma over here. So this gamma over here is actually one of the more important bits here. And what this is called the concretization function. We never really talked about this. So really, this just says, if I take this big symbolic shape over here, and if I actually enumerate all the possible points inside it, this is what gamma is. And if I just enumerate all the possible points, then I can compare to this f of x, because otherwise I would have some shape here which is symbolic, and the f of x is really just a shape, set of concrete points, and then this would be a superset, which is what you expect to happen. Okay, and that's all it is. And this is just the soundness that we always talked about, which is intuitive, right? It's you look at the concrete, the concrete green lines we had with the Relu, and we say, well, we always want to approximate it, and this is what we did. So this is not surprising. This is what happened. So soundness is one of the key aspects of abstract interpretation. But it is not surprising, but it is good to know what it is. Here I have some notation for our picture, right? And so this X here is a set of concrete values, right? It could be the set of all possible images, the variance of a given image that you want to perturb it by whatever L infinity distance you are allowed. The abstract symbolic element Z, as I already said, this would be some symbolic constraints that represents the concrete values. And gamma, this function that we talked about, is called the concretization function. So it just defines the concrete values that are represented by this symbolic element z. The points inside the polygon, right? The satisfying assignments, if you like, to z. The function f is the concrete transformer. This is our concrete Relu activations, or the affine activations. So it's funny, it's, they typically call it the concrete transformer, but in analogy to the abstract transformer that we discuss in the lecture. So this will be the concrete activation. And as we mentioned, what's very important here, because X can be a very, very large set mathematically, we cannot just compute the transform output set f of x. We cannot do this, right? We cannot just enumerate, which motivates us to define these abstract transformers, f sharp, which is what we did for the Relu and for the affine activations. We had the corresponding symbolic or abstract transformers f sharp. And so this f sharp works on the symbolic element z, the symbolic shapes that we get. And as I mentioned already, this f sharp must be sound, and this is what soundness means. Soundness, what does it mean? Okay. Okay, so this gives you a little bit of just a general picture of how we think about computation and abstractions of computation. So this would be the soundness, and really all it says is just if you apply the the abstract transformer f sharp on an abstract element z, like on some zonot of z, let's say, or on some DeepPoly element z, and then you end up with a set of concrete values that that correspond to the result. Okay, so here is the set of concrete values that correspond to the result, this gamma of the result. All right, so this gamma of the result must be greater. You must over approximate the results of just taking our symbolic shape z. So this would be, let's say, that the L infinity box around an image z, concretizing it to obtain all the images that we could have in that region, and then applying to each image the neural network f and looking at the entire set, right? So okay, so this is just soundness, what we already wrote on the previous slide. Okay. Now, exactness would be the case where these are equal. And so if you looked at the affine transformation, right, the affine transformation was exact for zonotop, for deep Z, and it was exact for DeepPoly. So it was exact for both of these relaxations, but it was not exact for the box relaxation because it was too imprecise. Okay. So it was exact there, right? For box, it loses precision there. Okay? And so this is what exactness would mean. Optimality, which is different than exactness, right? Really talks about the best possible approximation. And all it says is that if I say that some abstract transformer, let's say my Relu transformer is the best possible transformer, all it means is that there is not another transformer that produces more precise results. That's all it means. And this is what the mathematical equation says here. There is no other transformer f prime which produces results that are a subset of my best transformer, right? So we're only talking about sound transformers here. So these are all correct, but some are more precise than others. So if I say it's a, you have the best transformer, the best abstract transformer for Relu or for affine, well, there shouldn't be something else that is better, right? That includes fewer points than my f best, yet is sound, okay? In some cases, as we saw, there is no the best transformer, there is a best transformer. So there could be multiple best transformers here, right, that are non-comparable. And we saw that with the zonotop Relu relaxation, where we could just shift the slope up and down and obtain different approximation of the Relu. And we saw it here on the previous slides with the DeepPoly, where we had at least two approximations of the Relu, right? These two triangles that we saw there. Okay, so for zonotop, there really isn't, for example, a single best transformer, and similarly for the DeepPoly. Okay, there are multiple best transformers, And you can decide even dynamically during the analysis which transformer you want to pick, based, for instance, on a heuristic such as the area. Okay, so which transformer in the DeepPoly relaxation or in the zonotop, depending on how you twitch this slope. Okay, so this is just a glimpse, just a mention for you of abstract interpretation. And so what happened here is really saw several instances of abstract interpretation. It's funny that abstract interpretation also abbreviates AI, like artificial intelligence. And so several of these instances, Box is an instance of abstract interpretation. DeepZ, the zonotop, is an instance of abstract interpretation, and similarly for DeepPoly. So this gives you a very good working intuition and ability to work with abstract interpreters and to build these abstract sound interpreters that, some of which you already saw. It's a very rich area of abstract interpretation with many different branches and applications, not just in deep neural networks, but in many other domains. The theory is actually constructive. You can actually construct the theory given the F and the gamma. This is what I meant by constructive, because the F and gamma, by simplification, you can actually arrive at your abstract transformer F sharp, which is quite beautiful mathematically. Right, the particular branch of abstract interpretation that we looked at is called numerical abstract interpretation. So sometimes these are called domains, sometimes they're called abstract domains, abstract relaxations, numerical abstractions, convex relaxations, however you want to call them. But this is a particular branch of abstract interpretation where we're talking about numerical relationships between variables. So DeepZ, zonotop, box, octagons that we didn't look at, octagons, Polyhedra, DeepPoly, all of these are instances of numerical abstract interpretation. And the whole thing here is to trade off completeness and precision for scalability, for making the analysis scale to larger computations, larger program, while of course still being sound, being correct. Okay. Now, abstract transformers, as you see in the projects, and if you generally start working with these things, of these relaxations, these abstract domains, can actually be quite tricky to implement efficiently and correctly. There is often mistakes, subtle errors that arise. So one has to be very careful to make sure that even if you have the mathematical definition of what the correct Relu abstract transformer is, that you still implement it correctly, right? And so in practice, remember that, in general, remember that you have the two parts. One is the shape of constraints that the relaxation or the abstraction allows, and the other one is the abstract transformers that transform these shapes, right? And so typically the shapes that you have, right, are just some subpolyhedra shape, but like we saw already with the zonotop or with the DeepPoly, but the abstract transformers tend to be defined for the particular application-specific domain. So for instance, for the deep learning space, we had to define abstract transformer for Relu, for sigmoids. We didn't look at sigmoids or other activations like tanh, but we had to define it for affine and for Relu, right, transformations. So it is domain specific. So even though the shape may be quite known, some polyhedral shape, the actual abstract transformers are domain specific. So if you start looking at another kind of neural network architecture, which uses other activations, you need to define the corresponding transformers for DeepPoly and for the zonotop that we looked at, and for box. Okay, so a scalable and precise verifier, right, for neural networks or other computation really is just a combination of mathematics, right, being very careful with the mathematics, what sound means, making sure that, you don't make mistakes there, right, plus efficient algorithms for realizing this mathematical computation and coding. So this is covers quite a bit of ground in computer science when you're dealing with these abstract interpreters, right? Both algorithms, coding, mathematics, and so on, okay? So here's an interesting point that I wanted to mention to you that we didn't discuss in the lecture so far, is that one example of this, issue that you may have to worry about in practice is dealing with the floating point as well. Because the coefficients that we are dealing with here are real numbers, but in practice, the computers cannot represent the, they have some approximation of the real numbers unless you have some library that you're using, which may be very inefficient. And so many of these relaxations, many of these abstractions have to find a way to also be sound with respect to floating point. And if you look at the implementation of this, you would see that they often don't just keep the particular coefficients, for instance, that you have for the DeepPoly, but they keep an interval associated with these coefficients in order to be sound for the floating point, particular floating point that is used in the right, that is being used, like IEEE 754, for example, right? And to be sound with the different possible orderings that can happen, because floating point addition, for instance, is not associative. And so if operations happen in different orders, you may get different results, right? So you want to be sound and obtain the same result potentially for each of the possible orderings, okay? All right, so just a side point for you to be aware of when you're looking at the code, how these things are implemented. Okay, so this lecture concludes our discussion of deterministic certification of neural networks. We introduced another incomplete method, sound automated but incomplete method, the DeepPoly approximation, right? It's abstract transformers for affine and Relu for DeepPoly that we introduced. The affine transformer is exact, right? And the Relu transformer is approximative, just like in the zonotop relaxation that we looked at before. The nice thing about the DeepPoly relaxation is that the zonotop has the resulting approximation has a smaller area than the zonotop approximation for the Relu. So that's one of the advantages of DeepPoly over the zonotops, right? And we briefly looked at the general theory from where a lot of these ideas are coming from, which is the theory of abstract interpretation and specifically numerical abstract interpretation, and the mathematical definition of soundness, exactness, and optimality of abstract transformers. We don't need further for the course as far as abstract interpretation goes, but if you are curious, let me know and I can give you some pointers. So I hope you found this lecture useful, and see you next time.